And welcome again. This problem is in continuation of the last problem. In fact, in this problem we are going to remove a metal plate from a capacitor. And the credentials are here. The edge length of the square vertical plates of a plane capacitor of charge Q is A. So the area is being A square simply. And the distance between the plates is D, and well, you can see there is a D. Between the plates is a square metal plate of thickness D by 3. I guess this one is the square plate, and parallel to the plates of the capacitor. That's right. Find the work done by an external agent to slowly remove this metal plate of density rho. Its density is given, volume is given. Okay, so I can find the mass. Find the work done by the external agent to slowly remove this metal plate of density rho vertically from the capacitor. This is the problem, and we are going to solve it. So this is the metal plate. This is our famous metal plate. Okay, that's fine. This is our metal plate, and so the electric field inside the metal plate is 0. So the system can be considered as two capacitors connected in series, this one and this one. And if there is another capacitor, so I can write it 3 capacitors are connected in series. And if the capacitance of the capacitor taken as this plate and this plate only, let me explain to you. If I can take a simple capacitor as this one, charged plus Q and minus Q, and the separation between the plates is D, so its capacitor can be simply written as epsilon naught A by D. A is the plate area, that is basically in this case it will become A square by D. This is the capacitance of the plate. But if this capacitor is divided into 3 capacitors, each one the distance between them is D by 3 between each pair of plates, then their capacitances C dash, this, all of them will have equal capacitance, and I can write it as C dash. Then this C dash is simply equal to 3C, because you already know that capacitance of a parallel plate capacitor is inversely proportional to the distance between the plates. So this C dash is going to be simply written as epsilon naught A by D by 3, and that makes it 3C. These things are easily calculatable and can be easily understood, so I'm not going to think about it. I'm going to write down 3 things here. That is not 3 things, that just only 2 things. That we have a capacitor C between extremely apart plates, that is epsilon naught A square by D, and all 3 capacitors will have capacitance C dash, and C dash is equal to simply 3C. Just 2 things. And now I'm moving towards solving this problem, the real problem at hand. And I'm considering that the capacitance of the capacitor without the metal plate, that means empty house inside. I guess the electrostatic energy of the capacitor is so no. I would like to first find the electrostatic energy of the system before removing the metal plates. Metal plates are already in there, and in that case we have only two capacitors, and in between the electric field is present, because here electric field is equal to 0, so there is no electrostatic energy stored inside. Electrostatic energy is so stored only in these parts. So I'm going to write the electrostatic energy of the system before removing the metal plate, and that is equal to U naught, initial condition, equal to twice Q square by 2 C dash, because C dashes are their capacitances, and that will be equal to, if I can write C dash equals, that is 2Q square by 2 multiplied by 3C, and that becomes Q square by 3C, and that is Q square D by 3 epsilon naught A square. So this is the electrostatic energy of the system before removing the metal plates, and after the metal plates is pulled out, their electrostatic energy becomes U final, and that is going to be simply Q square by 2C, and that is Q square D by 2 epsilon naught A square. So this is the electrostatic energy of the metal plate is pulled out, and that is greater than, you can see UF is greater than U naught. You can simply compare them, and I can say one thing: when the capacitor, when we were removing the metal plate, the electrostatic forces will be acting in this direction, because we already know if we can place something in between the capacitor plates and place them in this manner, the electrostatic forces acting on the on that something inside the metal plate is in this direction. So I'm guessing, and the same thing is going to happen here, and the electrostatic forces during the removal of the metal plate will be in this direction, and so in this direction will be the gravitational force as well. So slowly slowly remove the metal plate from inside the capacitor, the external agent should apply a force in this direction. To slowly remove that means change in kinetic energy should be equal to 0. That is, work done by external force plus work done by electrostatic force plus work done by gravity should be equal to 0. And that means work done by external force should be equal to work done by electrostatic force and work done by gravity. And the work done by gravity I can write as mgA, because we need to pull out by a distance a, and since its density is given, so mass can be written as rho, thickness is d by 3, and area is a square. So this m, g and a, and this becomes a cube d by 3 rho z is the work done by gravity, and work done by electrostatic forces is simply okay, I can write WE, I would say it's simply UF minus U naught. So the total work done by the external agent is going to be 1 by 3 a cube d rho g plus 1 by 6 q square by d epsilon naught a square, and that is going to be your answer. Thank you very much for watching.